Good. We'll start with a talk by Wosiek, right? From planar quantum fields, from planar quantum mechanics to planar quantum physics.
Thank you. So, of course, I would like to thank organizers for everything and would like to tell you about our recent works with Gabriele Veneziano, which we have been doing for the last 2 years, maybe 2.5 by now. And the main theme is actually trying to solve the bound states, to find the masses, eigenstates of the Hamiltonian, using the Larchen simplifications. So exactly in the planar limit. And being here in the kingdom of the Newton, I don't have to tell you how important the bound state problem is, from all sizes all the way down to pions and protons, and I also don't have to tell you how difficult it is. So we are all aware of that, but there is this one thing, one item, which is the Larchen, and which I have learned only recently, that it is actually able to do tremendous simplification. So we don't know actually if it helps all the way down to QCD, but we certainly had the fun to study some smaller systems, and then we eventually move in that direction. So let's begin with quantum mechanics, and this is already quantum mechanics which is related to gauge theories. So let's think about QCD at infinite volume, or rather Young-Mills. This Hamiltonian is for supersymmetric Young-Mills, and reduce it in space to one point. So what is left? We are left with a quantum system which has as many degrees of freedom as there are components of vector field and as there are fermions. In particular, this is supersymmetric system in 4 dimensions, 3 plus 1, so we have 2 Majorana fermions or 2 Weyl. And these systems are, this idea is also not new. It was actually first conceived by Bjorken in 79. These potentials which are derived from gauge interactions are very cute. They have these famous flat valleys. Therefore, there is a mixing of discrete and continuous spectrum. So actually, this potential was even listed by Feynman on his board as a cute problem to solve. And then the model came again, which was used by Martin Luscher to set up the small volume expansion, which was very useful for lattice calculation. And then finally, it acquired huge publicity, let's say, at the end of last millennium. This is here, it's SU2 with epsilons, yeah.
As far as I know, this is really Martin Hartmann who was quantum mechanics.
Yes.
And if he was here, he would be really angry.
He would be very angry. Well, but I think, no, they were not earlier than 79.
Huh?
They were not earlier than 79.
He was in the 80s. He plans for the...
But I agree.
Whatever.
He is always very angry if you don't say so. So I appreciate. I experienced that few times. Anyway, so how do we solve? For us, what was why these systems were of main interest is that actually we could solve them. We could solve them numerically, quantitatively to the very end. There are some systems which we also could solve analytically. But so how do we solve it? We solve it in as simple way as possible. We set up a Fock space, and this is sort of a mnemonic notation. States have to be gauge invariant. They are traces of gauge, and so on. But we just construct a basis, which is basically a Fock basis, and then we calculate matrix elements of Hamiltonian, diagonalize, and that's it. But of course, the problem is that even the simplest Hilbert space for single harmonic oscillator is infinite. So if you want to do numerics, you have to cut it. So we cut it by gauge invariant total number of quanta, and in higher dimensions also rotational invariant. So this is a nice cutoff, and then the important thing is if these eigenvalues converge with the cutoff. And actually they do converge. What? So this is the spectrum of the SU2 supersymmetric Young-Mills quantum mechanics. We got this way with Massimo Campostrini. This was before Veneziano era, let's say. And it has it's very rich, and it would take me all this time to discuss this spectrum. I'll only show it has supersymmetry. It has this feature of continuum. These wings are supermultiplets. They come actually, degeneracy supersymmetric degeneracy comes nicely after levels have converged. And there is this embedding of discrete states, these are these red states, into the continuum. So there are all kinds of other things, and I don't have time to discuss it. So the next thing was Larchen. This was n equal to 2. So So now Gabriele got interested and he said, hey, why don't we just use large n literally? So we evict from all these bases all the traces, which are all the states which are products of traces. We keep only the single trace operators in the states in the basis. And this is tremendous simplification. You know, the number of these states is much bigger than this. But yet this is what everybody is doing. Yes? So let's take it seriously and calculate bases, diagonalize Hamiltonian only in this sector. So then we came across the simple toy model, which is supersymmetric, doesn't have any indices. These are the supersymmetry generators, and there is the Hamiltonian. And when we diagonalize this in this way, then this system, we thought it is just a toy model, but it kept us for a long time because it's very rich again. It is a distant cousin of supersymmetric Young-Mills in 1 + 1 dimension, but it is not really Young-Mills, because pure Young-Mills in 1 + 1 would just be trivial, would be just this FA dagger. So this is something else, something more involved, and it has non-trivial structure. It has a phase transition at the Hopf coupling lambda = 1. It has exact duality between these two phases, strong and weak coupling phases. Finally, we found analytic solution in one of the sectors. It splits into many sectors of fermion, of conserved fermion numbers. So for fermion-less sectors, there is analytic solution, simply in terms of hypergeometric functions. And finally, at infinite lambda, it is infinite with the Heisenberg model, or spin chain, with this famous anisotropy parameter = 1/2. And then, it's not the end, it is also identical with the Q-bosonic gas, cube on a lattice. Q-bosons are just like bosons, but the creation operators don't, when they act on the state with given occupation number, they don't multiply this by this famous square root of n + 1. So that is why they are called Q-bosons. And actually they satisfied Q-default commutation rules, and there are some limits. In Q = 1 limit, they are usual bosons, and our case is just Q = infinity limit. So then we found that therefore there are hidden supersymmetries in these statistical models. And we talked to many experts, and none of them actually knew that there is hidden supersymmetry of this Heisenberg model until Gabriele came here, and we learned that actually this was known. But still this is not known, and actually this system is pronounced to be not soluble. And via all this chain of equivalences, it is actually solved. Okay, so this was the old story. And now we move to field theory. So there was one lesson from quantum mechanics which I didn't have time to elaborate on. This idea of single trace dominance, of the cutting to the sector of single traces, doesn't always work. It works only if Hamiltonian annihilates the empty vacuum. So this seems actually as a very difficult condition to satisfy. So one may think that this is end of the story. If you want to look for some unphysical Hamiltonians which satisfies this, then what is use of it? But actually it's not the case, because there is a very physical situation where this is satisfied, and this is the light cone formulation. Because as we know, the light cone, there are no zigzag graphs, there are no bubble graphs. So there are in the vacuum on the light cone. So this is empty, therefore light cone Hamiltonian really annihilates the empty Fock state. So this was very nice. We got excited again, and then we looked into the literature, and of course we were not first to discover that. We found ourselves in a very good company. So the first person who noticed actually this problem was Charles Thorne, the same Thorne who actually formulated the light cone in 1977. Even earlier there was Hopf model, which is QCD2 in 1 + 1. And then there is all this list. Now Hopf model is very nice, of course, and beautiful. Hopf has solved for all these bound states numerically, but it has one simplicity. It is large n, therefore, and it has fermions in fundamental representation. Therefore, it cannot have higher multi-parton states. So there are only two parton states. The bound states of Hopf were only made of two constituents, and this is exactly because 1/n, and of fundamental nature of these fermions, of quarks. So for that reason, people actually generalize this, and they ask, they define, they wonder about Young-Mills with adjoint matter, and this matter was was either scalar, and then you can think about it as reduced Young-Mills from 3 dimensions, or fermion, put in just no supersymmetry, just fermions in a joint representation. And then later on, people actually made supersymmetric models from this. And then in 4 dimensions, light cone was pushed by Wilson and Wozek and Hiller et al. And Stan Brodsky, as we know, is doing this for all the time. So this is basically the short history. Now how this goes, how the light cone discretization works. There are 2 ways actually to attack the problem quantitatively. One is called light cone discretization. On the light cone you have this p plus variable which is conserved and which is composed of n partons with positive fractions. Important thing is that they are with positive momenta. Important thing is that p is positive. So then if you want to do it on the computer, you discretize, you replace p by integer k, which we play the role the cutoff, and then you look for all the partitions of this k into integer submomenta. And actually they are natural. One excludes from the construction 0 momenta, and then one only recovers the 0 mode when k goes to infinity. Because k does actually 2 things. Yes, k limits, because of positivity, k limits number of partons, and k also discretizes the momentum axis. So at fixed k we are distant from 0 by 1 over k, and we eventually want to close. All right, so how do we proceed? How people proceed? We just decide on your k, you generate all partitions. These partitions give you states in the same way as in this quantum mechanics, except that there are many more of them. You calculate matrix elements of the Hamiltonian, and you get energies. However, there is another way. And this is what I would like mostly to convey to you, because I think it was not looked upon carefully enough. And there are very beautiful equations there. And since you are experts of complex equations, so take your chance. So one introduces different cutoff in practice, but one does it in the continuum. There is no discretization. So we attempt to solve this eigenequation. H is just p plus p minus. It's light cone Hamiltonian, so this is mass square operator. So then we decompose eigenstate into its Fock components. These are the wave functions. And then the eigenequation looks like that. This is m squared times phi, and this is Hamiltonian acting on this state. And what Hamiltonian can do? Hamiltonian is the 4th order polynomial, so it can actually scatter 2 partons, it can create 2 partons, or it can absorb 2 partons. There is also 2-body term which I omitted. So these equations, and so this is actually a hierarchy of equations. These amplitudes are just coefficients of these operators, simple functions, mainly they contain just powers. They are just simple Coulomb propagators, basically. And then there is a convolution which is integral with respect over all these z fractions of partons involved in the process. But the main thing is that actually this hierarchy is infinite hierarchy. Yeah? So we have to, this couples every multiplicity with every multiplicity. Well, not every second in this case, this is for scalar theory, but in any case, it's infinite system of equations. So now, short 2 words about interpretation. This is, of course, eigenequation, and you can leave it at that, but it has very simple interpretation. Proton is just invariant under all these elementary processes. Yes, if 2 partons scatter, there is this infinity of partons boiling in the bound state, and it doesn't matter if they scatter, if 2 of them are absorbed, if 2 of them are created, according to the Hamiltonian, one has to get the same state. Yeah. So this is like if we had a dirty car. If you throw some mud on a dirty car, it's again dirty car, or if you clean it with a dirty clothes, it's again dirty car. So basically, this is it. Then these equations are fundamental. There are other equations which are very popular, which go under the name of Diglap equations, and we have the L representative here. But these equations are sort of effective. They give us evolution in the transverse momentum parameter or in the virtuality. And this equation, so they, for example, have a cutoff, Q0, above which they can be applied. These equations, in principle, thank you. These equations, in principle, are exact. So they contain these Diglap equations. And finally, nowadays there is a popular issue among people who are solving these equations, for example, there is this problem of abundance of gluons at low x. And people know unitarity is broken, so people are thinking, and there are intuitively thinking about new equations which have absorptions of gluons. And these equations have absorptions of gluons by definitions, except that they are on the level of the quantum amplitudes, not on the level of the probabilities. Okay, so now the cutoff. Cutoff has to be, so we have to, if we want to attack this numerically, we have to cut multiplicity. And as you remember, as I said, in Hopf case, Nmax was 2 because of the fermionic representation. So this is a sample of results. This is mass of the lowest state as the function of k, of 1 over k, so you want to reach 0, and this is how this light cone discretization works, and this is the result of these equations. And usually people are able to, with biggest computers, they are able to reach here, to something like k equal 20. The reason why I was able to plot this was that I did it only for the two-body. I only considered partitions of k into 2, and these equations were also only for 2 partons. So this is type of, you see that this is very, actually the behavior around here is very difficult, and one has to have both of these things. I don't have more time, so I will not tell you about it, how the equations look like actually. I'll tell you about the recent thing. These equations, for example, if you take scalar matter, there is a problem there. The masses are infrared divergent. So what was done earlier, people just called this thing renormalized mass, and they went ahead, either with light cone discretization or with this solving this hierarchy of equations. But somehow, if you want to go to supersymmetric, first of all, infrared renormalization somehow doesn't sound well. Yes. And then, if you think about supersymmetric theory, this would require introducing counter terms. So then you may break SUSY. Yes. So the question is, how is it really happening? And we expect that actually it is happening differently. You don't have to, it is happening dynamically. These infrared divergences are cancelling dynamically. This is example of the solution of the, look just at these two curves, two sets of points. This is the solution when light cone discretization, when we cut ourselves only to the two-body sector. And this is when we have all of them. And you see that this has a tendency, this looks as if it was flattening, and this is growing. So this we interpret as sign of this logarithm because we didn't include higher sectors. And these, we included some of them, okay. We included some of them, and this works all right. So actually our proposal is that it is like a, so this is not usual this is not usual infrared cancellation because Hamiltonian itself is divergent, and this is problem for the bound state equations. Usually when we have infrared problems, we define inclusive quantities and things are finite. Yeah? So this is, nevertheless, we suspect that divergences cancel dynamically, and we have, I want to show you in this 1 minute which is left, a quick non-abelian toy model which is Bloch-Nortzwig inspired. There was an ancient reference here from 1932 of Heisenberg. This paper is from 1937 and is also quoted until now. So the model, which is some modification, is very simple. It's just separable. It's sum of modes, but there is a divergence. If you take current, it's emission of soft quanta from current, from classical current, and if you take current this way, there is the same phenomenon as in the whole thing. So but we know what's the solution. So Hamiltonian is divergent, but solution here is that if you define the rest quanta, which are these Bloch-Nortzwig transformed, which are nothing but coherent states in this case, then the Hamiltonian is finite, and the eigenvalues are just occupation numbers in this case. So we actually expect that the same thing must be happening in our case. And here I gave you an example of what we have, and this is work in progress, it's not finished. So these are these integral equations in that case, and actually, since they are for this separable problem, one can solve them exactly. Nota bene, this is the only case I know of one can solve such hierarchy of equations. But anyway, and this is numerics. So here are the first 3 levels as the function of epsilon, depending on the multiplicity of partons I include. So here I have cut it up to 2 partons, 3 partons, 4 partons. Thank you, I'm done. So you see, what we see is as what we expect. There is a singularity in epsilon, but this singularity is dampened and dampened when we go to higher and higher multiplicity. So the question is of the game. So this should be a benchmark for our interacting situation. We are looking for some plateaus which would develop in epsilon. We cannot go with epsilon to 0, but we are looking for these plateaus. And these plateaus should be compared with the light cone QCD. And then this would give us a handle to see these masses from both ends. Thank you very much.
I have one for this supersymmetric quantum mechanical model.
Yes.
Lambda goes to 1 over lambda.
Mm-hmm.
Can you show that?
Yes. From these solutions you can show it.
So you have a
We have analytic solutions in terms of these hypergeometric functions, and you see that they have this symmetry. But we have actually noticed it before. We noticed it from the symmetry of the Hamiltonian. We saw it numerically, and then we came across this solution analytically. Okay.
good. If that's not the case, then thank Professor Wosiek.
Thank you.